Let's look at the range of a linear transformation. When you work with the change of variables theorem, in many cases, you're trying to describe a region R that's more complicated as a more simple region S, using a transformation that you develop. And so you'll see examples of those in the work problems. But what I wanted to do now was just an example of where we're given a transformation and we just want to see what the range of the region R would be. So I wanted to go through this and just show you some ideas that you may remember from your college algebra class. So like I said before, we're asked to determine the range of the region R under the given linear transformation. So here's the transformation right here. That is x is equal to 3u plus 2v and y is equal to 3v. Now, before we talk more about this transformation, here's the region R. Again, a triangle with vertices 0, 0, 3, 0, and 2, 3. Now, when we want to move from R to S, in your notes, you see that we write this with the t minus 1 as an inverse transformation, because the notation utilizes the transformation from S to R as the t transformation. So I want to use the same notation here. But we can actually write this linear transformation as a matrix. So we can have the 3 and the 2 as the top row and 0 and 3 as the bottom row, since the coefficient of u here is 0. And then we can just utilize matrix multiplication. So this would identify the transformation from R to S. Now, in order to see what happens to this region, we first can know that any type of line segment will be taken or mapped into another line segment. And really all we have to do is focus on the vertices to get a really simple picture. But before we do that, we need the inverse transformation. So what I've done here is I've given you a little extra information. Remember, when you have the 2 by 2 matrix A, B, C, D, you can easily compute the inverse using this formula. That is 1 over the determinant, which is AD minus BC times this matrix. This is worth knowing. The A and the D switch places, and then the B and C get an additive inverse. Now, of course, if you don't do that, you can always solve the system by straightforward means, which can be very easy. But this is just very useful and something you may use later. And so now, when you do the determinant of this matrix, you simply get 9. So we have the 1 9 and the 3 and the 3. Of course, we can't see that interchange. They're the same entry. And then the additive inverse of 0 and 2, which gives us this when we multiply each entry by 1 9. So our new matrix is 1/3, -2 ninths, 0, and 1/3. And we call that the matrix T. So now, like I said before, we don't have to worry about the line segments. They get mapped into line segments. So we can check what happens to the vertices to get a quick answer. So now 0, 0, again, you can frame all of these as matrix multiplication. So when you multiply here, you get 2 entries of 0 and 0 here. So you get the ordered pair 0, 0 or 0, 0 in the UV plane. Now for the ordered pair 2, 3, which we have right here, we can do the matrix multiplication. So we get 2/3. And then of course the 3 will absorb into the 9 to give us a -2/3. So the top entry becomes 0. And then downstairs we get 0 plus 1/3 times 3, which gives us a 1. So we have the ordered pair 0, 1, 0, 1 in the UV plane. And then for the last pair, 3, 0 in the XY plane, we apply the matrix. So we get 1/3 times 3, which is 1. Then, of course, a 0 entry. And then downstairs, we get 0 plus 0. Again, 1, 0. So we get the ordered pair 1, 0 in the UV plane. So now we get what appears to be a much simpler region, these being the new vertices. So now, when we plot these, the 0, 0, the 1, 0, and the 0, 1, the intermediaries are just line segments. Now, you can rigorously go through all of this and show that these are actually the ranges of these line segments here, but you don't have to do that. You can utilize this fact that I've given you just to save a little bit of time. And so now when you look at this region, you would say, well, how would we describe this? Well, first, if you were analyzing a region without a given transformation, you can just go ahead and look at the slope of this line. This would just be the rise over run. So we have 1 divided by -1 to give us a slope of -1. Then, of course, you can use this point. So B would equal -1 times U minus 1. And then if you distribute the -1, we have B is equal to 1 minus U. So now as you move in the B direction, you have a lower limit of 0, and of course the upper limit of 1 minus U. And then clearly U runs from 0 to 1, which we have here. So this particular description here is very simple. So again, remember, with change of variables, what you're trying to do is take a region that is actually quite complicated if you had to describe it and transform it into something very simple. Now, like I said before, in this particular example, we're given a transformation, so we get to work with that. But in the examples, you can see how you can use simple algebraic techniques to develop your own transformation to create a simpler range, that is to transform R into something simple. So as you see here, as we move from R to S, we have a much simpler region, and we are done.